Section 11-4, Analysis of Variance. The idea for the section is to introduce one-way analysis of variance. Analysis of variance is sometimes called ANOVA, A-N-O-V-A, from the analysis of variance. The calculations here will require a distribution that we haven't seen before, and we're not going to go into too much detail for finding the test statistics and things like that. The idea is for us to just use technology. So we're going to use technology to find the p-value and then try to conclude the same results, come up with the same conclusions that we've had before about rejecting or failing to reject a null hypothesis. And so we're just going to brush on this idea and then be able to do problems in this section. So we're going to cover part 1 only, and that's the basics of one-way ANOVA. So just to reiterate, the definition is a method. ANOVA is a method of testing the equality of 3 or more population means. And the way we do that is we look at their variances. Now, if you think back to chapter 9, we were performing hypothesis tests where we tested 2 means, and now we're going to extend that where we have 3 or more samples that we're going to test. So the one-way analysis of variance uses one factor or one treatment, and this is going to allow us to distinguish between the different populations. So what do we need? We need the populations to be approximately normal. We need the populations to have similar, statistically similar variances or standard deviations. We need simple and random samples, and samples are going to be independent from each other. And then the last bit here is that different samples are from populations that are categorized in only one different way. So an example of this would be like comparing the final exam scores for the different semesters, and so the different semesters would be the one way we're going to categorize these different samples. So the procedure is going to be the same setup for our null and alternative hypothesis. The null hypothesis will assume that all of the means are equal to each other. Okay, so that's the general setup. We will use StatDisk. We'll use a TI-83 calculator, or we'll focus on that in our class. And then we're going to look at the p-value. And then we're going to reject the null hypothesis or fail to reject it. So when we reject the null hypothesis, we're saying that we are rejecting the hypothesis that all the means are equal to each other. So we just have to take caution in the idea that the means may not, if the means aren't equal to each other, we're not saying which mean is not equal to the big group. We're just saying one of them is not equal to each other. If you want to test for which specific samples have a different mean, then that's the stuff that's covered in part 2 of the section, which we are not going to do. So here's an example where we're looking at the IQ scores. So the performance IQ scores are listed below, and the significance level of 0.05 test the claim that the 3 samples come up from populations with means that are all equal. So that's going to be our null hypothesis. So what we're saying is that we're categorizing these IQ scores from children into 3 different groups. One group would have low blood lead level, another group would have medium blood lead level, and then another group, a third group, will have a higher blood lead level. So these will be our different groups, and they're categorized by the blood lead level. So here are some statistics that we can see from each of those samples. We have a sample size of 78 and 22 and 21, and then the means are 102.7, 94.1, and 94.2, and we're essentially comparing those. We're going to use the sample standard deviation or the variances. Actually, we're not going to dig into that too deep because we're going to let our technology take care of that for us. It's also good to identify any probable outliers that are going to mess up the data set. A quick requirement check: the 3 samples come from samples that are approximately normal. 3 samples have standard deviation that are not statistically different. We can treat the samples as simple and random. Samples are independent from each other, and then there are 3 categorized. The 3 samples are categorized into one single factor, and that is the amount of lead in their blood. So our setup will be the null hypothesis is the means are all equal to each other. The alternative hypothesis says at least one of them is different. We don't know which one, but at least one. We have a significance level, and let's take a look at some of the technology outputs. In Statistic, this is how your output would look like. We focus mainly on the p-value, but it's also good to look at the test statistic. This is the F test statistic that we'll take a little glimpse on. The SS and MS would be some values that might be important for further analysis. Excel also does ANOVA, and we get the same p-value, 0.0195, and the F value is 4.07. And then we get the same SS and MS values. Note that there's degrees of freedom here. The degrees of freedom are different from, there's actually several degrees of freedom here. One is degrees of freedom between the groups, one is the degrees of freedom within the groups, and so it's 2 and 118, and then they have the total degrees of freedom. Minitab and StatCrunch will yield the same results. And here is SPSS and JMP, and also our graphing calculator, and we focus our P. It's actually our p-value, that's 0.0195. Alright, now that we've gotten the p-value of about 0.02, we compare it to 0.05, and 0.02 is less than 0.05, so we can reject the null hypothesis. So as we reject the null hypothesis, we can say that there's evidence that the 3 samples come from populations that have means that are different. So we've rejected it. We can say that the means are not all the same, but we cannot conclude formally that one particular mean is higher than the other. Although we can kind of see that the first mean looked like it was higher. The low blood lead level had a higher mean, but we can't formally conclude that unless we do further tests from the part 2 that, again, we're not going to go over. So let's focus on the p-value in test statistics. We got large values for the test statistic will result in smaller p-values. That's very similar to the chi-square test. So when we have a large p-value, we reject the null hypothesis. The F test statistic is a little bit more complicated, or the F distribution is a little bit more complicated than any of the distributions that we've seen. So again, we're not really going to go over that. One thing to note, though, there's this idea that we're testing the variations between the samples, and we're testing the variations within the samples. Here's just a snapshot of the relationship between the F test statistic and the p-values. Again, it looks similar to the chi-square distribution with the right tail test, and so That's really all we need to go by. What is the F test statistic that we're getting here? The F test statistic is essentially a ratio or a fraction where we take the variance between the samples and the variance within the samples. Okay, so another caution: the test when testing for equality of 3 or more populations, we're going to use the analysis of variance. That's ANOVA. Don't use the multiple test statistics that we learned in chapter 9. So ideally, we can think about looking at this, not ideally, but one approach to look at this would be to compare 2 samples at a time, and then we would have to do about 6 comparisons. That's not the way we test for differences in 3 or more populations. So we're going to use the analysis of variance for that. Okay, so I will conclude the lecture series, this section and the lecture series at this point. Again, there's a part 2 that you can look at. You're more than welcome to examine on your own. But for now, we're going to be done with analysis of variance. We're just going to do the basics. Just plug it in your calculators and figure out the p-values. Okay, look out for some examples for the analysis of variance in the sample video homework assignments, homework help. Okay, good luck.